Hello everyone, welcome to PicoGenius.com, where science, electronics, and microcontrollers converge. In today's video, we're going to delve into the world of PID Control, and it's going to be using a Raspberry Pico Pi. We'll be implementing a PID controller to regulate the temperature of a heater. I'll walk you through the entire process step by step, so let's dive in. Some of the uses for PID control include industrial applications like controlling temperature, levels, and flow rates. In addition, modern aircraft use PID control to adjust their surfaces for smooth, accurate flight operations. First, let's understand what PID control is. PID stands for proportional, integral, and derivative control. In our demonstration today, there are three control outputs that will work together to maintain a desired temperature by reading a 13-bit I2C temperature sensor and adjusting a heater's power output using pulse width modulation. Let's take each of the control methods and see how they work together. Proportional control looks at the difference between a set point and the current control variable, or temperature, and adjusts the control output accordingly. In this example, the set point, or the desired output, is set to 1. That is represented by the red dashed line. When the control variable, which is represented by the blue line, is 0, there's a large difference between the set point and the control variable. This difference is referred to as the error. If this was a temperature control system, then the set point would be the thermostat control. The control variable would be the temperature sensor feedback, and the control output would be the heater control. With a large error, the heater control would need to be turned on aggressively, like at 100%. And then the turn-on percentage would be decreased as the control variable gets closer to the set point. So first we must determine how much the proportional control will influence the total output, or the total control output. This is done by establishing a proportional constant. The proportional control output is defined as the error multiplied by the proportional constant. As you can see, the control variable gets closer to the set point as the proportional constant is increased. This is because the proportional control output, which is the heater control, is larger with larger proportional constants, thus driving the control variable closer to the set point. You'll also notice that the control variable becomes increasingly unstable, or has more of a tendency to oscillate, as the proportional constant becomes larger. This is why in the tuning process we have to pick a proportional constant that gives us a maximum gain with minimum oscillation. You'll also notice that there is always an offset between the control variable and the set point with proportional control. This is because there must be an offset for the error term to exist, so that the proportional output can be calculated. So we're going to use integral control in our PID scheme to fix this offset problem. So the integral control output is defined as the integral constant multiplied times the integral term. Now the integral term is a running sum of all past errors over time. It accumulates the errors, giving more weight to the persistent error in the proportional control variable, or essentially moving it toward the set point. As you can see, the integral constant increases the offset between the control variable and the set point is eliminated. You'll also notice that the stability of the control variable decreases with an increase in integral constant. Here again, this is why during the training or the tuning stage, we have to pick an integral constant that reduces the offset while minimizing the control variable oscillation. Okay, so now we're going to use derivative control to eliminate the oscillations in the integral control curve. The differential output is defined as differential constant multiplied by the differential term. Differential term is the rate of change of the air and is calculated as the difference between the current air and a previous air. The purpose of the differential term is to provide a control action that's proportional to the rate of change of the air. It helps prevent the system from overshooting or oscillating by applying a damping to the control action. As you can see, as the derivative constant increases, the oscillation is damped out. Increasing the derivative too much will result in overdamping and sluggish system response. So it's important that you pick this so that you don't have an overdamping situation. So putting the proportional, integral, and derivative control outputs together and tuning their respective constants result in optimum control of the control variable, as you see here. So with an understanding of the PID algorithm, let's take a look at the hardware block diagram for the PID control system. We have a microcontroller that's reading the heater's temperature and controlling the heater using a PID control loop. As the temperature is captured by the microcontroller, it's transmitted to a data acquisition device along with the controller set point temperature. The current temperature and the set point temperature are then plotted on a PC. This allows us to look at the heater's response to the PID control loop. It also allows us to tune the PID loop by dynamically changing the proportional, integral, and derivative constants to optimize the operation of the loop. Now let's take a look at the hardware schematic. We have a Raspberry Pico Pi, a DS18X20 temperature sensor. We have a heater that's controlled by pulse width modulation and a data acquisition device to plot the system response. The DS18X20 sensor monitors the temperature of the heater, and the Pico adjusts the heater power using a pulse width modulated signal. The 4N35 opto device and the field effect transistor amplify the pulse width modulated signal from the Pico to control the heater. The Pico creates two other pulse width modulated signals that are processed by low pass filters, which are nothing more than 10K resistors and 47 microfarad capacitor. One of these signals represents the set point being requested by the Pico, and the other is the temperature of the heater. These signals are processed through the data acquisition device and plotted on the PC. The loop constants, case of P, case of I, and case of D, can be tuned through Thonny, and the system response can then be observed. This is the hardware setup for the PID controller. As you can see, I have a Raspberry Pico Pi that's interfaced through the opto device and the FET to control the heater element. On the top of the heater element, I have the temperature sensor, which is a serial link back to the Raspberry Pi. And then finally I have the Raspberry Pi creating pulse width modulated signals that are going in as analog signals to the data acquisition system. And then that goes out through the USB and is plotted on an application on the PC. I've taken 4 6-volt batteries and wired them for 24-volt operation, and that's what's used to to power the heating element. Okay, well, let's look at the code now. We're going to write a Python script to implement a PID control on the Raspberry Pico Pi. The script is going to read the temperature from the DS18X20 sensor. It's going to calculate a PID control output and adjust the heater's pulse width modulated signal accordingly. So the first thing we need to do in the program is to import the libraries that we need to create the pulse width modulated channels, and also the object that we need to read the DS18X20 temperature sensor. So this code defines 4 pins on the Pico Pi. Pin 2 communicates with the temperature sensor. Pin 15 provides the pulse width modulated signal to control the heater. Pin 13 provides a pulse width modulated signal representing the temperature of the heater. This signal is filtered and plotted by the data acquisition device. Pin 9 is a pulse width modulated signal that's filtered to plot the set point by the data acquisition device so that we can compare the two. These lines of code create an object that's associated with their respective I/O pins. These objects have characteristics and behaviors. For instance, the heater underscore PMW equals machine.pmw creates a pulse width modulated object that can have its duty cycle controlled on pin 15 of the Pico. Other objects, temperature underscore PMW and set point underscore PMW, are also created and associated with Pico pins 13 and 9 respectively. This code creates a sensor object that can be used to communicate with the DS18X20 temperature sensor over pin 2 of the Pico. Sensor.scan is a method. Think of a method as a subroutine of the object. In this case, the object is called sensor. This method scans one wire bus to determine the address of the temperature sensor to be used later in the program. These 5 lines of code define the temperature set point, the proportional, integral, and differential constants for the PID loop, and the pulse width modulated frequency that defines the timing for the pulse width modulated signal. Now we initialize a few PID variables, and then we enter a loop. The loop begins by calling a method in the sensor object, which is sensor.convert_temp. This initiates conversion from the temperature sensor. Once the conversion is complete, the temperature is read using a method sensor.read_temp and is equated to the variable temperature in the program. So now that we have the temperature, we have to calculate several variables. The air is the difference between the set point and the temperature of the heater. The PID control outputs must be calculated as well. The proportional output is the proportional constant, case of P, times the air. The integral control output is determined by first accumulating the integral air and then multiplying the integral air by the integral constant, case of I. The differential output is determined by first determining the rate of change of the air. This is accomplished by taking the difference between the current air and the previous air. This value is then multiplied by the differential constant, case of D, to determine differential control output. To get the total control output, the proportional, integral, and differential control errors must be summed. So these lines of code are responsible for adjusting the pulse width modulated values that control the heater that do the temperature visualization and the set point visualization on the PC. Then these lines of code set the duty cycle for the pulse width modulated signals for the heater, temperature visualization, and set point visualization. The pulse width modulated signals are represented using 16-bit scale, where the values range from 0 to 65,535. Keep in mind that the duty cycle represents a percentage of time that the signal is on compared to the total period of the pulse width modulated signal. Here, all the pulse width modulated variables are printed to the Thonny terminal so that we can see the PID's control process or progress. Last but not least, a new previous error is established and a small time delay is generated before the next iteration. So now we'll go and look at a live demonstration of the PID control system at work. Okay, here we are in front of the data acquisition screen. I have my program running in Thonny right now. As you can see, my set point is at 50 and my temperature is varying around 50, 49.7, 50.4, something like that. And you can see that represented on the screen right here. The gray line is the set point, the blue line is the control variable. You'll notice that the PID loop is operating the heating element. The heating element's just a 24 volt bulb that has the 13-bit temperature sensor on top of it. So what we'll do is we'll change our set point. Right now it's at 50. I will go in and change that set point to 70, and we will see what the response of the system is then. Here we go. It's been reset. Notice the bulb is coming on to drive the temperature, and you can see the set point has come up here, and in my okay, the set point has come up, and my control variable is climbing and converging with the set point. Not a lot of overshoot. It's acting very well behaved right now, in part, because if you look at the program, I have my proportionality constant, my integral constant, and my differential constant. My proportional constant set to 6, my integral constant set to 0.008, and my differential constant set to 30. I established those numbers in a tuning procedure to maximize the temperature convergence, the time of the temperature convergence, and minimize the overshoot, and also maximize the accuracy. And as you can see, it's tracking pretty good. Really, in a system like this, you probably would want to use different constants for going from high temperature to low temperature than you would from going from low temperature to high temperature, simply because the cool down rate and the heat up rate is going to be different, because I turn on current to heat the sensor up, but I'm limited to how quickly I can cool it down, because it just cools down naturally on its own. If I were to have a fan blowing on it or something like that, I could control its cool down rate. Now you'll notice when I set the temperature back to 50, that that the slope of the cooldown is going to be less great than the heat up slope. And the reason is, of course, is because the cooldown, I can't control the cooldown. I could actually, if I put a little water on the sensor, you'll notice it'll drop the temperature quicker. But I don't have an air conditioner or anything on that sensor, so I can't really control its cooldown rate. Also, we'll see how it does about latching on to that lower set point. I suspect there will be a little bit of offset. This is caused by the integral function. The integral function has accumulated some air on its way down here, so I'm seeing that on the offset. I can put additional code in there to take that out. Another thing I can do is, if I just reset the system quickly, you'll notice that the integral air goes away and I'm back up to the set point. So there is a function that I can put in here that will eliminate that accumulated integral air. But anyway, with that eliminated, you can see that that the temperature is tracking the set point pretty good. I'll bring it back up to, let's say, 60. And we'll see how well it does. Okay, the set point comes up to 60. Here comes the control variable. And it looks like it's going to converge pretty closely with the set point, with absolutely no offset. So my tuning constant's pretty good right now. You know, later on I'll do another video on how to actually tune the control loops. So there you are. PID control using a Raspberry Pico Pi microcontroller. If you found this information interesting or useful, then please subscribe and give me a thumbs up. It helps a lot to keep me motivated to create content for you guys interested in science and electronics. And lastly, if you're interested in reproducing this experiment, you can get all the information that you need at www.picogenius.com. On my website, I've provided this PowerPoint, the schematics, the Python code, and the spec sheets for everything that you need for this project and for others.